Hello, hello, everybody. Well, we are finally here. So, I have been promising since the very first lecture, when I warned everybody about how difficult this class was, that when we got to this chapter, the stuff on sequences and series was probably the hardest stuff in this class, and this was probably the hardest class that anyone who isn't a math major, right, takes, as far as math goes. Some of the upper division math classes are harder and more fun, but for engineers and physicists and so on, this is probably the hardest math class they take, and now we're to the hardest part of it. Congratulations! So this is hard stuff, but it really is a lot of fun when you get the hang of it. The reason it's hard is it takes a tremendous amount of practice to just get good at doing these sort of problems. So we'll see as we go along that if you do enough homework and you work really hard, then you can get the hang of it and do great. The problem is people tend to either do really, really well or really, really bad on this material. So let's get ready to dive in. One quick comment before we I show you the first animation here. I do want to mention that throughout this class, almost all the slides that I've done have been strictly my work. But Dr. Reagan Higgins is one of my really good friends in the math department. Did some really, really, really cool improvements to some of the slides that I use, and so I wanted to shout out to her in this video that some of this was actually her work. So I want to start by explaining why we're going to bother talking about series, or at the very least, why I think this stuff is cool. The the stuff we're going to do is really hard, and it's going to take a long time to slog through it to get good at it. So I think it's important before we even start to go, why would anybody care, right? So Zeno was an ancient Greek, lived thousands of years ago, and he had several paradoxes. And the most famous one is this one. And they all essentially came down to the fact that something is fundamentally screwed up with the universe. And so here's Zeno's most famous paradox. So here's a little man, and I want him to walk to the other side of the screen, or at least be animated and travel over there. And of course I can do that, right? I've programmed into the computer there. I moved him all the way there into the screen. But Zeno said, he shouldn't be able to do that because, well, think about it for a second. If he's going to walk all the way across the screen, then first he's got to go halfway, right? About that far. So half of the screen. And of course, I can make him do that. He went halfway. But now he's got to go, well, the rest of the way. Right? But let's think about this the way we did just a second ago. He's got to go half of the rest of the way. In other words, that's, half of what's left is a quarter. So he's got to go a quarter of the way now. So, okay, does that. Well, once he's done that, he's got to go half of what's left. So half of the quarter that's left would be, of course, an eighth. Right? So he has to go that eighth. Then he has to go half of what's left, right? That's a 16th that's left. So, of course, he goes that far. He has to go half of what's left. That's a 32th. Then he has to go half of what's left and half of what's left, and so on. And so you see, as you start adding up these numbers to see how far he's actually traveled, he had to go half the screen, then a quarter of the screen, then an eighth of the screen, and so on. And this was Zeno's problem. He said, what in the world can that possibly mean? How do you add up infinitely many numbers? You keep adding on more and more and more. You got to get infinity for the answer, right? I mean, you can't just add up infinitely many numbers and not let it get the sum keep getting bigger and bigger and bigger and go off to infinity, right? That's kind of a good point, right? I mean, how in the world can we add up infinitely many numbers? Now, we have seen a tiny hint of this before where we tried to look at an infinitely long area when we were doing improper integrals. And this gives us a hint that maybe there's something going on here that will make sense. In fact, the way we did those improper integrals is almost exactly the same idea we're going to use to make sense of this. But maybe you see that this is a non-trivial question, right? And you can see why this boggled the Greeks' minds that didn't really have a good idea of a limit. What do you do if you try to add up infinitely many numbers? How can that even make sense? Okay, so we need a definition, right? I've been throwing around the word sequences and series all this time. And so we saw what sequences were already. Sequences were just lists, essentially. That was our informal definition. A series is a sequence added up. So it's just like we were doing a second ago. The sequence would be a half, a fourth, an eighth, a 16th, a 32th, and so on. That's our sequence. The series is what you get when you add all those infinitely many numbers up. Right? And again, this is important to understand the difference, right? So if I were doing this in a face-to-face class, almost every class I would say a sequence is, and make the entire class shout a list. And then I would say a series is, and then the entire class say a list added up. So if it makes you feel better, you can stop now and wave your arms in the air and say that along with me. Later on in the videos, we'll have something called a power series, which is something else again. And we'd add that to our mantra. So in the normal run of the English language, it is easy to get these confused because if you stop and think about it for a second, the most common place I use the word series is when I talk about the World Series. Not this has anything to do with the Cardinals and them having not been there for a while or anything. So the World Series is a sequence of games, right? One game after another, all the way up until you get to possibly at least 4 and possibly 7. So we tend to use the words sequence and series in normal English usage interchangeably, right? So for our purposes, though, a sequence is, everybody together, a list, that's right. Okay, a series is, everybody all together, list added up, right? Exactly. Okay, that's our informal definition, and that's what you really want to keep in mind. But to answer Zeno's problem, right, we need a more formal definition, and we'll need to keep this definition in mind too as we solve some of the problems we had. So how do we actually go about talking about adding up infinitely many numbers? Here's what it means. A series converges if the sequence of partial sums converges. Okay? And this is the point where everybody goes, okay, you've lost me, right? I'm done. Now I see why this stuff is so hard. And this is a weird looking definition, right? Because a series converges if some sequence of partial sums. What? So, okay, so we need to unpack all this because it's really important to understand this definition. So we're going to just go through this slowly until everybody feels okay with what we've done here. Or at least if you don't feel okay, you can rewind this and watch it as many times as you need to until this all makes sense. So first thing to see is a bit of notation. So a series is supposed to be a list that's added up. So we would write, AK. We've used that before as a sequence, right? So this is our sequence, the AK sequence. And this big sigma, of course, is sigma for sum. And we've seen sums before, and we did Riemann sums and so on. And the subscripts here, k equals 1 all the way up to infinity, means that we start with a 1, then we add a 2, then we add a 3, and then we add a 4, all the way out to infinity. We add all of them up at one time. Okay? And so what does it mean to add all those infinitely many numbers together? Well, that will converge, right, if a new sequence converges. Okay, so what is this Sn? Well, that Sn, right, notice that's a sequence. S sub n is a sequence. Okay? And how do I figure out what S sub n is? Well, I partially add up my series. Notice this is big sigma that says k equals 1 here, up to, oh look, just n. Okay, so what does that mean? What's S1? Well, S1 is what I get when I add up A1 up to A1. So it's just A1. So S1 is just A1. What's S2? It's what you get when you add up the first 2 terms in the series. So it's A1 plus A2. S3, the third sum, would be what you'd get if you add up A1, 2, and 3 altogether. And of course, the fourth element in my sequence of partial sums, which would be S4, that's what I get if I add up A1, A2, and A3, and A4, all 4 of those together. So, and of course, that would give me a sequence, and it's a list, and I know all about lists, right? We've studied sequences already. I know all about whether a sequence converges, so I can tell whether that list of numbers, Sn, converges, and if it does, then I say the whole series converges. So, okay, so we've taken something we didn't know anything about, this idea of a series, we've turned it into something we do know all about, which is sequences. Okay, so still that may not be terribly enlightening, right? So let me give you my explanation of how this works. almost everybody has been to either the grocery store or maybe to Walmart, and you go and most such stores now will have a big monitor so you can see what things are as they scan the prices, so you can see what they're charging you and so on. So I want you to imagine that you have pulled up to the checkout counter at the Walmart, and you have infinitely many things in your cart. Now, again, if you're a poor college student, you may not be used to having to buy infinitely many things in your cart. I can assure you that when you get to have 3 kids and they're all running around behind you sticking Cokes and Snicker bars and whatnot in the cart as you're trying to check out, you will understand what it feels like to buy infinitely many things as you're trying to check out. so we've got an entire sequence in my cart, right? The things in my cart are all in there. There's A1, there's the first thing. There's another thing in my cart that's A2. There's another thing in my cart that's A3, and so on. And I need to buy all this stuff. I need to check out and pay the price for A1, the A2, and so on. So here's what I do. I take the first price, A1, and I run it across the scanner and put it in the bag. And what pops up on the screen is the price, right? A1. Okay. Then I grab the next item, run it across the scanner, put it in the bag, and what shows up on the screen now is not just the price of A2, but down in the corner, it shows my running total so far, right? How much I'm going to have to pay for this. Of course, they do that so you'll know whether you're out of money or not, right? Before you've scanned everything in your cart. But I've scanned my second item, and so what shows up in the bottom is my subtotal, right? What it cost for A1 and for A2. Well, that's exactly what this sequence of partial sums is. It's those numbers that show up in the corner of the screen. It's the first price of the first item. Then the next number in the list is the price of the first item and the second item added together. Then the third number that shows up in the corner is the price of the first 3 things added together. So when I scan the third one, that number switches to be the sum of the first 3 items. Then I grab A4, and the number switches to being S4, the sum of the first 4 items. So this is an idea that we all know, right? Because we've all scanned stuff at the self-checkout at the Walmart or been there while that we went through the line where someone else checks it. I really, really like the self-checkout line because being a mathematician, that it makes me inherently antisocial. And so if I can scan myself out without having to talk to another human being, that's much nicer. so I hope this makes sense. And if it doesn't, rewind it and listen to it again, and I'll beep for you some more as we go through scanning these items in the cart. But that idea of the subtotal is exactly what this sequence of partial sums means. It's the list of subtotals that show up as we scan each item, right? And of course, the total cost of everything in the cart, right, should be the limit of that list of subtotals, right? As we go further and further and further down into the cart, right, we scan more and more and more items, then that list will eventually converge to the final price of everything in the cart. So that's what it means to add up infinitely many numbers. It means you add up finitely many of them, and then add up a little more, and then add up a little more, and add up a little more, and see what that list of subtotals, of partial sums, adding up part of it, what that list of subtotals converges to. Okay, so we desperately need an example now, right? So here's one. So we have the sum from k equals 1 to infinity of 1/2 to the k. So my sequence that I'm adding up is the sequence 1/2 to the kth power. And my series is what I get if I add up all those numbers. So if we try to write this out, and this helps a lot to write things out in this long form, when k is 1, right, k is equal to 1 is where this starts. I'll have 1/2 to the first power, so I get a half. Then when k is 2, right, k switched to be 2, I get 1/2 squared. Of course, that's a fourth. Then when I get to k equal 3, I'd get 1/2 cubed, so that's an eighth, and so on, right? I'd get 1/2 to the fourth power, 1/2 to the fifth power, and so on. And I add all of those up to make my series. Okay. So what would my sequence of partial sums look like? Well, S1, the first partial sum, that's when I grab the first item, a half, scan it. I get a half. I grab the fourth and scan it, beep, and my subtotal isn't a half or a fourth. It's what's going to be a half plus a fourth, which is what I hate doing fractions in my head. Was that 3/4? Okay, so that's the next item in the list of subtotals. Right? I grab the third thing in the cart. That's an eighth. Beep. I scan it, and I get a half, an eighth, a half, a fourth, and an eighth all added together. That's the third subtotal, or the third partial sum, and so on. Right? We keep scanning and adding more and more to the list. Now, it's a good question. I keep adding more and more numbers here, right? Zeno would say, wait a minute, how do I know that's going to converge, right? Why should that sequence, this list of subtotals, not go off to infinity? Because it's getting bigger and bigger every time, right? It's definitely an increasing sequence. Well, we know that it's possible for increasing sequences to converge, right? They converge if and only if they're bounded above. So maybe this guy does converge. And it turns out that it does, because this is an example of a whole family of series called geometric series. So I want to show you the full glory of a geometric series, and then we'll see when a geometric series converges. Right? So a geometric series looks like, well, the one we just did. You don't have to start at 1 the way I did. You can start anywhere. So maybe you start at 0, that's maybe the most common, or at 1, or at 3, or at 50 million, doesn't matter. That's what my n there is. So the first term in my geometric series would be some number a times some number r raised to the kth power, and we start when k is equal to n. So the very first term is ar to the n. Then we go to n plus 1, and so we get ar to the n plus 1. In other words, what's happening is we're multiplying by r every time, just like in this last example, right? Our r here is a half. So we're multiplying by a half every time. And the a in this example is just 1, because this was a nice simple example. So this is a geometric series where a is 1, r is a half, and we start off when k is at 1. Right? So that would be the n equal 1 in the current example. A lot of times we'll call r the common ratio because we're multiplying by the r in every term. Okay, so that's the geometric series. Now, when will this geometric series converge? It's actually really, really, really easy to tell. We love geometric series because it's super easy to tell when they converge. And so here it is. The theorem is this entire geometric series, right, adding up all infinitely many terms, will converge, right, whenever the absolute value of r, that common ratio, is less than 1. So in that last example where r was a half, that's perfect. That one guy will converge. And we'll see what it converges to in just a second. Because we have a formula for what it converges to in our theorem. It's always ar to the n over 1 minus r. Okay, I know what you're thinking. Crap, it's a formula. Didn't we have enough of those when we were doing integrals? well, it's actually not that bad. If you look at ar to the n, what is that really? Right? It's the first term. Okay? So this is really the first term over 1 minus r. Okay? And this will converge when the absolute value of r, right, is less than 1. And of course it diverges every other time, right, when r is anything else. Right? So again, the way to think about this is this thing converges to the first term, first thing in the list that we're adding up, right, the first thing we scan, divided by 1 minus that common ratio, assuming that the absolute value of r is less than 1. And otherwise, it diverges. So it's super easy to tell whether it converges or whether it diverges. I'm going to go ahead and show you why this works. Okay, this is not something I'd ask you to do on a test, but it's something that's really, really, really cool, and it's pretty easy to understand if you write it out the way I'm going to. So it's worth listening to just so this is not just a magic formula for you. Okay, so how does this work? Well, suppose as an example here, I'm going to start with my geometric series out starting at 0. So notice it starts when k is 0. So when I start writing out my terms, I'll get ar to the 0, which of course that's r to the 0 is just 1. So the first term will just be a, right? Then the next term will be ar to the first power, then ar squared, and so on. And I'll add up the first ever how many of those. Now notice the geometric series has this cool pattern, right? I just go up by an extra r every time. So something cool happens if I take that and multiply that whole sum by r. You see what'll happen. I'll get AR. Oh wait, I already got an AR. Let me write it so it lines up. I'll get AR and then AR squared and then AR cubed and eventually AR to the n. And of course, AR to the n that I had here gets multiplied by r and it becomes AR to the n plus 1. So I'll line it up where it's sort of shifted and you can kind of see what happens. But now this is written this way, screaming out for somebody to subtract this, right? If I came along and subtracted these two, then, well, on the left side, I'd get Sn minus Rsn, so I could factor out the Sn, so it'd be 1 minus R Sn. On the right-hand side, right, look at all this. I'll get an A, but then all this other mess in the middle, right, will cancel. And that leaves me with just, well, the last term minus, because I'm subtracting, minus AR to the n plus 1. And now if I divide by 1 minus r on both sides, that's where my 1 minus the common ratio is going to come from. I end up seeing that all that partial sum business really came down to the first term minus AR to the n plus 1 over 1 minus r. Now, if you did a lot of number sense or UIL math in high school, you might have run across this formula before in geometric series before, because this is a really common number sense or sometimes on the math exam sort of question to add up like the first 20 terms in a geometric series, and there's the formula, right? Just use this. But for our purposes, remember what we want to do is let n go off to infinity, right? We want to take the limit as n goes to infinity. Well, okay, I put a limit on the SNs. I need to move this over and put a limit here, right? So that I haven't said something that's silly. Always be careful with notation and write it correctly. Okay? Now, what happens when n goes off to infinity? Well, the only n that happens is right here on this power of r to the n plus 1. And so what happens? Well, if r is a number like a half, then raising it to a power makes it smaller and smaller and smaller, and so it'll go away. And this whole term, AR to the n plus 1, will go to 0, and it'll just disappear. If r is a big number like 7, raising 7 to a power makes it bigger and bigger and bigger, and this thing will diverge and go off to infinity. So that's exactly what happens. We get that very first term, right? That a right there was our very first term, over 1 minus the common ratio, if and only if that absolute value of r was less than 1. Because if you remember from old homework we had, r to a power will converge, right? It'll go to 0 if and only if the absolute value of r was less than 1. Okay, let's try another example or two here. Here is 2/3 to the k. We start k off at 0. So our common ratio is 2/3. Our a there is just 1. So if we start writing out this term by term, when k is 0, we'd get 2/3 to the 0. So that's 1. That's our first term. Then we'd have 2/3 to the first power, then 2/3 squared, and so on. We need to add all those up. And our common ratio is the 2/3. That's what's getting multiplied, right, each time. And 2/3, well, the absolute value of that is 2/3, and 2/3 is less than 1. So what we get when we add all those terms up is the first term over 1 minus the common ratio. And the first term is 1. So I get 1 over 1 minus the common ratio, which is 2/3. And now you have to do some fractions. Yuck. Okay. 1 minus 2/3 is 1/3 in the denominator, but that's in the denominator, so you flip it and it becomes 3. So the only thing hard about this was just doing the fractions right at the end, right? Not making a silly mistake with the fractions. So this is really not hard at all, right? Once we know what we're doing, right? We look at the r, check its absolute value and see if it's less than 1. If it is, then we know this series converges, and we know what it converges to. It'll always be the first term over 1 minus the common ratio. Let's try another one. So here is 1/2 to the k, right? So this one starts out when k is equal to 1. So when we start writing out our terms, we would get 1/2 to the first power first. So that's a half. Then a half squared, and then a half cubed, and so on. So, of course, again, our common ratio is a half. That's less than 1. The absolute value of a half is half, which is less than 1. So this will converge, and it'll converge to the very first term, which in this case is a half, right? Again, this is why it's really important to just start writing these out. Look what k is equal to, plug in k equal to 1 right there, and write out these first few terms. So the first term is a half, so we'll get 1 half over 1 minus r, which again is a half. And so, okay, this is cool because 1 minus a half, I can do that. That's a half. It cancels with a half in the top, and the whole thing just converges to 1. That's actually really cool if you stop and think about it. We've seen that before, right? We saw exactly this series before. If you remember back a few minutes ago, that was the series we had in Zeno's paradox: a half plus a fourth plus an eighth. And so, does that add up? Yes, that converges, right? In fact, it converges. We went half a screen, a fourth of a screen, an eighth of a screen, a 16th of a screen. All that adds up to, remember from this one whole screen, right? And so that's exactly what Zeno's paradox should have had us do. If we go halfway, then a fourth of the way, then an eighth of the way, and add up all those parts of the way, we get one whole way. Okay. Here's a slightly more algebraically ugly looking example. It's still a geometric series, but maybe we want to do a little algebra to convince ourselves of this, because this has 2 to the k plus 1 right there. And so how do I make that look like, r to the k, and figure out what the ratio is? Well, what I can do is take this 2 to the k plus 1 and make it 2 to the k times 2, right? I've separated that out, factored off an extra 2. Now I take that 2, bring it around and stick it with my 4. So that'll make an 8 and leave me with 2 to the k over 3 to the k, which of course I could put parentheses and make that 2/3 all to the k. And then it's kind of obvious what my ratio should be, right? If I write it out each term, maybe that's even easier, because k is equal to 2, and I'd get 8 times 2/3 squared. Then I get 8 times 2/3 cubed, and then 8 times 2/3 to the fourth, and so on. So my common ratio is 2/3. The first term is 8 times 2/3 squared. So since 2/3 is less than 1, I'll get 8 times 2/3 squared over 1 minus 2/3. So same thing again, right? The rest probably getting sick of these examples, right? Because they're pretty easy once you see how these go. Here's one more that's a little algebraically ugly. So again, the only hard part about this one was just making sure that we could get 32/3 by simplifying that fraction, right? Hey, here's one's a little uglier because it has that minus 1 to the k in there along with everything else. Now you could try doing algebra like I did a second ago and factoring out a 4 and a 5. What I'll do here is I'm just gonna do this and try to figure it out on the fly. Let's take the 2 and just plug in 2 and start writing out the term and see if we can figure it out from the list. So when k is equal to 2, I get -1 squared. Okay, that's just going to be 1. Then 4 to the 2 plus 1, that's third power, and 5 to the 2 minus 1, that's the first power. So I'd get plus 4 to the 3 over 5 to the first. Okay, that's my first term when k was equal to 2. When k is equal to 3, I get -1 to the third power, so it'll give me a minus. Then I'll get 4 to the 3 plus 1 over 5 to the 3 minus 1. So there we go. Then when k is equal to 4, oh look, we're back to -1 to the fourth power, which is 4 minus 1s, which is positive, so we're back to positive again, and 4 to the fifth over 5 cubed. And you can see the pattern now, right? What's happening is each time I'm multiplying by, well, it looks like 4/5, but if you look at it carefully, it's -4/5, right? Because that -1 here is making the sign shift every time. The next time I'd get a minus when I went here, right? I'd have -4 to the 6th over 5 to the 4th. So my common ratio is -4/5, right? And the common ratio can be negative. And remember, we've always talked about having the absolute value of r. Well, here's an example. R was negative, so the absolute value of -4/5 is +4/5. That's less than 1. We're good to go. We need the first term over 1 minus the common ratio. So what's my common ratio? 4 to the third power over 5. So that goes in the numerator. 1 minus the common ratio. And remember, the common ratio here was negative 4/5. So this becomes 1 minus negative 4/5. So when I simplify that, I get 1 plus 4/5 in the denominator. Okay, I'll have to do a little algebra, tinker with that, and eventually we would get 64 over 9. Okay, let's try one more. So this has a 7 and then 3 to the k over 2 to the k minus 1. If we did a little algebra to simplify this, we could take that 2 and bring it out, and we would have 7 times 14, and the extra 2 in the denominator then would let us write it as 3 halves all to the k. Okay, so what's my common ratio? It's 3 halves, right? Is the absolute value of 3 halves less than 1? No, 3 halves is bigger than 1, so I don't have to do any weird fraction stuff, right? My common ratio is bigger than 1. This diverges, and we're done.